Hello students, the purpose of this video is to get you acquainted with radicals and the properties of radicals. When I look at a radical, I want to make sure I know the different vocabulary words that tie in with radicals. And the very first one we're going to look at is the word index. This number tells you the root that you're working with. When there's no number and all you see is your radical symbol, then you know that you're working with a square root symbol. But if we're working with anything else like a cubed root or a fourth root, you have to have that index number. It's super important to remember to always include your index number. So if you're ever working through some problems, and maybe you have a third root or a fourth root, you want to make sure that you carry that index value through each step. The next vocabulary word is the radical symbol. So the actual little squiggly house type symbol is your radical symbol. And then we have our radicand, which is actually the number inside of your radical. So it is the number that is being rooted, and that is called your radicand. Now, when I look at some properties of radicals, there's two that are very helpful to us. The very first one talks about when you have more than one radicand, so two terms being multiplied together inside of your radical, you can actually separate them, and this makes it a little easier for you because you can separate and take the root of them individually. A lot of times this helps you with simplifying. For example, let's say that you are dealing with the square root of 16x. I can separate this into the square root of 16 and the square root of x, and I know that the square root of 16 is equal to 4, and so that allows me to simplify part of my problem. I can't do anything with the square root of x. So this is really good when you're trying to simplify. The second one says the same exact thing, but this deals with fractional values. So when you have a radicand that is a fraction, you can go ahead and separate your radical on top and bottom and simplify separately. So these are super helpful. You'll use these throughout the class. So as always, I encourage you to pause this video as we are going to practice simplifying these radicals. So I encourage you to practice on your own before watching the solutions. So looking at the first one, the square root of 8 times the square root of 3, I have the square root of 24 because 8 times 3 is 24. And then I like to simplify using the tree method. And so I'm going to break down 24 into two numbers that I know multiply into 24. So 12 times 2 multiply to 24. I'm going to break down 12 into 6 and 2. And I'm going to break down 6 into 3 and 2. And the goal is for ends of my stems to all be completely simplified, meaning the only multiples are 1 and itself. And once I have that, I'm going to go ahead and I'm going to draw this little brace here, and I'm going to write out the ends of the stems. 3 times 2 times 2 times 2. And I'm going to create groups. And I'm going to create my groups based off of the type of radical that I have. So in this case, because I am dealing with the square root, that means that I want to make a group of the same number of 2's. So I'm trying to create pairs. So here is a pair. And when I create a pair, I can take that value to the outside of the radical symbol. The reason why is 2 times 2 is 4, and the square root of 4 is just 2, right? And so essentially I'm doing rules of radicals, but just thinking about it a little different. If I can't make any more pairs, like I don't have another 3 and I don't have another 2, I'm going to re-multiply those values together and keep them underneath my radical symbol. So my final answer would be 2 and then square root of 6. Looking at the fourth root of 48, I'm going to do something similar here. I'm going to try to think of two numbers that get me to 48. And I know that 12 times 4. And I'm going to break down 12 into 6 and 2. And I'm going to break 6 down into 3 and 2. And I'll break 4 down into 2 and 2. And when I list out my numbers, 3 times 2 times 2 times 2 times 2, which are the ends of my stems, in this case, I'm actually looking for groups of 4 because my index value is 4. And so luckily, I do have a group of 4. I have 4 2's right here. And so I can take a 2 to the outside. And I'm going to keep the 3 underneath my radical symbol. But notice that what I have written in green is not correct, because I did not bring over my index value yet. So you want to make sure you bring over that index value, otherwise your answer is not correct. Now, the next two that I'm going to look at are actually really awesome rules that talk about the root, the index value on a radical, and the exponent. When they are the same value, they actually end up canceling each other out so that I'm left with just what's in the inside of my radical. And I'm going to give you an example why this is true, and it actually works better with the second one down here. Keep in mind that this is saying we have the seventh root of x to the seventh. So that's 1, 2, 3, 4, 5, 6, 7. And I know that I need to make a group of 7 because that is my radical number. So everything is a group, and I take just an x to the outside. So again, you're noticing that as long as the index value is the same as the exponent value, all that I'll have left as my final answer is what's on the inside. And that's true for both of these problems. I'm going to look at the cubed root of 24. I'm going to actually skip the 121 just for the sake of room. But I'm going to go ahead and look at the cubed root of 24. If I looked at the cubed root of 24, it looks similar to the one we did first, right? But the difference is now I'm doing the cubed root, so I'm going to be looking for groups of 3. So again, I'm going to break this down. I'm going to use different numbers this time. I'll use 6 and 4, and then break down to 3 and 2 and break 4 down to 2 and 2. And so my final stems are 3 times 2 times 2 times 2. And I need to make a group of 3 in this case. So I have a group here. I'll take that to the outside, and I have the cubed root of 3 left over. And I just want you to notice how that looks a lot different than the first solution we came up with when we had the square root of 24. So your index value truly does impact the problem that you're working on. Now, another thing that we'll do with radicals is combining like terms. And similar to variables, you know, if you have a variable, they have to look exactly the same. So an x and an x can be combined. An x squared and an x squared can be combined, but we don't add or subtract an x and an x squared. We can't combine those. So similar to that, radicals are the same. You're looking to make sure your radical, the index value, and the radicand are exactly the same. So you see here in this first example, my radical and my radicand are the same. So I'm going to perform the operations of the outside values, 5 minus 2, which is 3, and bring over my radical portion. Now on the second example, I have the square root of 48, and then unfortunately I have the square root of 27. So at first glance, these are not the same. But you always want to start out by trying to simplify and see if you're able to rewrite the problem. So I'm going to come over here, and I have 2 square roots of 48, and I'm going to see, can I break this down? So 48 breaks down into 12 and 4, and 12 breaks down into 3 and 4, and 4 breaks down into 2 and 2, and this 4 breaks down into 2 and 2. So I have 3 times 2 times 2 times 2 times 2. And in this case, there was already a 2 on the outside. So I'm going to draw an arrow to bring that down because it's already outside. And I need to try to make groups of 2. Well, here's a group, so I'm going to multiply a 2 to the outside. Here's another group, so I'm going to multiply a 2 to the outside. And I would have the square root of 3 left over. So 2 times 2 times 2 is 8 square roots of 3. Which means I can now rewrite this portion of the problem as 8 square roots of 3. And then I'm going to try to do the same thing with the other portion. So I have 3 square roots of 27. 27 breaks down to 9 and 3, and 9 breaks down to 3 and 3. I'm going to bring down the 3 that was already there. And I'm going to write out the values 3 times 3 times 3, and know that I need to make groups of 2. So I can bring a 3 to the outside with the 3 that was already there, and then I have the square root of 3. And 3 times 3 is 9 square roots of 3. So I can rewrite the second portion as 9 square roots of 3. I'm going to go ahead and bring down my minus sign. And now what's super, super awesome is I have the square root of 3 and the square root of 3. So I have created like terms and therefore can go ahead and combine these. 8 minus 9 is negative 1 square root of 3. And you can also write that as negative square root of 3. I will allow you to do the last example on your own, but again, you're going to try to simplify both of these terms. And what you're going to find out happens in this example is that you're able to simplify, but you still can't combine terms. And that's okay. You want to simplify as much as you can, and if you can't combine, then you can't combine, and that's okay. One last thing I want to talk about is the relationship between rational exponents and radicals. So sometimes instead of writing things in a radical form, I may want to write them in their fractional form. So I want you to notice that the exponent underneath the radical that is inside will always represent your numerator in exponent form. So again, looking at numerical example, this 3 is on the radicand on the inside, and I'm going to put that in the numerator when I write it in its exponent form. Whereas I'm going to take the index value that I have and write that as the denominator value. So again, with numbers, my index value is actually my denominator value in exponent form. As always, I hope that you found this video helpful. If you have any questions or concerns, please don't hesitate to reach out.